This is Kamal Sarma. Today I am going to discuss about bending moment and shear force. These two forces, bending moment and shear force, they are very vital for design of beams. And we'll be discussing about simple beam, that is determinate beam, where we can find out the reactions, because we need to find out the reactions of a beam to draw the bending moment shear force diagram. What is bending moment and shear force diagram? It is the graphical representation of the shear force and bending moment and different section or different portion of the beam. Okay, so this is how the bending moment and shear force diagram, because by looking at the bending moment diagram or shear force diagram, the designer knows where the maximum value is, how much it is, and he has got a complete idea of the behavior of the structure, how these forces are acting on the beam. Okay, so what is the beam that we need to discuss? Beam is a member which is, in most of the cases it is horizontal. It may be vertical also, but it's a horizontal, and load is applied laterally. So this means this is supported like that, pin jointed, because I told you that we will be considering only the simple beam. Okay, so the loads are applied laterally. This is the beam. If it has a cross section, maybe the beam cross section, always the lateral dimensions is less than the length, much less. So if it is a L, the L is much bigger than breadth and depth. The load is applied laterally. This is the axis. This is the, if you call the plane, x plane. So if you have, this is your axis, x-axis. This is your y-axis. This is your axis, direction of the x-axis. It applies in the direction of y. One more important point, that you see that there is direction upward is positive and direction to the right is positive. So here what happens, these forces we always consider acting against the axis, that's a negative direction, and the whatever reaction generated here is upward, that means it is positive. Reactions are positive, the forces acting downward is negative towards the gravity. So now the question is, this when you apply some loads there, it have action on the beam. First of all, there will be two reactions at the support, plus the beam will, two things happens to the beam. One is something like this. This is the beam, this load is there, this try to shear it. One part going up, one part going down. You do not see that way in reality, because there are some other factors are affecting, which doesn't allow to move. If you take a shock pencil, if you put the pressure like that, it will break like that. But here in the beams, it has got strength, it doesn't allow to move in this direction. There's the stresses in this direction because of the bending, and that's why we do not see it directly tearing off. That is called shear force. We call it shear force. That means it tries to shear this beam section. That is called shear force. And another factor, another thing happens to that, when you put the beam, it tries to deflect. Something like this. If you have a beam, if you put some loads, it will try to deflect like that. So what happens when it tries to deflect? You'll see in normal cases, with the simply supported, there will be angle here, theta 1, theta 2, and deflection, say y at the middle. So any force multiplied by a distance, suppose you want to find out the moment at this point, this force and all these forces you have to multiply by the respective distances, x1, x2, all these, okay? So it is force multiplied by this distance is moment, okay? You know that. Force multiplied by distance is moment, and that moment which causes bending is bending moment. It bends. That counts bending moment. Okay. So what is this? Now we are going to do the diagram. How we have to draw the diagram. Okay. So the diagram is graphical representation of the shear force and bending moment in a beam. Suppose if you have a beam, if you have a load, whatever shear force here, if you draw that with the help of a diagram, I will explain how to get the diagram. So this is called shear force diagram. This diagram is a graphical representation of the shear force at different positions of this or different location of the beam. So this is obviously upward, this is positive, this is negative. I will tell you how to calculate that. And if you find out the graphical representation of moment will be something like this. So at every point we will find out the moment. If you connect the dots, it will be like this. Something like this. So it is considered as positive, upward. You draw it upward, positive. So I will tell you how to, this is called bending moment diagram. So first of all, you know the shear force, the shearing it off, bending, it bends, and the graphical representation of all these in a beam along its length is your shear force diagram or bending moment diagram. Shortly it is called SF diagram for shear force. For bending moment it's a BM diagram, in short form. Okay, don't be confused. All right, now, as I told you earlier that we need to have a determinate structure. You can do it for indeterminate structures also, but main problem there is finding out all the forces. That means all the reactive forces, all the reactions. Okay? So, but in a determinate structure, what are the determinate structure? Determinate beams. Determinate beams are, one is simply supported. That means you have one end is hinge, the other end is roller support. This is one of the simply supported beam. This is called simply supported. And there is another one you can easily find out the reaction, because here this is one reaction here, say VA. I explained that in my previous class. It is HA. This is VB. So that means 3 reactions. We can easily calculate that. We can easily find that. The second one is a cantilever. If you have a cantilever beam, that means one end, the beam is fixed at one end, another end is free. Suppose you have a load like this. Then what happens? Here is the moment. This try to rotate, then this fixed end prevented the rotation. So their moment develops. This is a reaction moment. Then there is the vertical force. There is the horizontal force. Suppose your load is something like that. Another load, W2. This is W1. So because of this, some horizontal force is there, vertical force is there, and the moment there. So these 3 forces, these 3 reactions, we can find out the values. And for drawing the bending moment and shear force diagram, we must have the reaction, otherwise it will not possible. So in some complicated structures, somehow we find out, to draw this, somehow we find out the reactions, and then easily we can find the bending moment or shear force diagram. Now, when a beam bends, one thing you should remember. When a beam bends, suppose you have a simply supported beam like this. This is, I am actually drawing not a line diagram, actual beam. The shape of the beam is something like rectangular, say. Concrete beams are, reinforced concrete beams are rectangular. So it is a rectangular shape. So there is it will bend like this. The top part, when it bends, simply supported. Top part is, you see, it is reducing in length from here to here. From here you can see. So when you reduce something length, that means the molecules are pressed inside. So this is compression on this face. And other side, at the extreme end, here you see that on this side, they are elongating, their length is increased. So this side, well, that means the molecules are separating from each other. So they are pulling. So it is tension. So if you draw the diagram, suppose this one, here, let me draw it at a bigger scale. This is the cross section. So at a point, somewhere in the middle, you'll see this remains the same. The original length and from here to here length is same. It doesn't change. Neither it is pulled out, neither it is compressed inside. Okay, so that is called neutral axis. So it is neutral in bending. That is the meaning, neutral axis. So somewhere in the middle, in a shape like that, it is exactly at the middle. Center of gravity as the middle, and it will be there. So this is, if you draw the bending stresses, it will be something like this. It is linear. So this is the neutral axis. So here is the compression, here is the tension. One thing the sign convention is very important in structural analysis. Sign convention, what's positive, what is negative. So compression we consider always as positive, and tension we always consider as negative. Okay, So positive and negative, this is neutral. This is how the moment acts, and this is how the shear force stress is developing. It is in the middle, the maximum, and two ends is tending to going to zero depending on the shape of the beam. It may vary with the shape of the beam, but still the maximum is at the middle or at the neutral axis. Just reverse. Okay. Now let us talk about the diagram itself. How can you find the moment, bending moment and shear force diagram in a beam? First of all, let us consider one simple beam again. The line diagram. Okay. Now, suppose this is, I am considering numerical value, so that will be easier for you. Okay. So here I am considering it is say 10 meter. Those who are using American system, consider it is 10 feet. But feet and meter are not equal. Okay, you should know the 1 meter equal to 3 foot 3.4 inches. They are not equal. But I am changing in the unit so that the unit doesn't matter. But I am just showing you so that you can visualize, you can see how it is. So 10 feet, assume it is 10 feet or 10 meter, but they are not equal. Now, 1 meter equal to 3.34 inch. And suppose we have a load at the just exactly at the middle. So at a 60 degree, we have a load of 10 kilonewton, or you can say 10 kip. Kip means kilopound. So don't worry about this. Those who use this SI system, the 10 kilonewton, you know what it is. And for those who use the American system, it is 10 kip, kilopound. Okay, they are not equal, of course, because 10 kilonewton is equal to 2.25 kip. So they are not equal. So I'm just doing it for my convenience. I don't like to convert it and make you do it twice, the calculations. Okay? Now, so this is at the middle. This is 5 and 5. Now, first of all, we have to find out the reactions. Now, think this is the inclined load. The part of this will go along the axis. This forces going along the axis doesn't cause any moment or any shear force. Axial force doesn't cause any shear force. So you have to ignore that. So axial force, here the reaction will be, only this force is there, direction will be summation of horizontal force equal to 0. We apply that, and that way it is 10, the angle is 60 degree, 10 cos of 60 degree. So 60 degree cos of 60 degree is 0.5. So it is 10 times 0.5 equal to 5 kip or 5 kilonewton. Kilonewton or 5 kip, whatever whatever you consider. Now, this component of this force in this direction is that much, and what is the vertical component of this force, which will cause moment, bending moment. So this is 10 sine of 60 degree. Sine of 60 degree is, this is equal to 10 times 0.866. So this will be 8.66 kilonewton or kip, whatever it is. 8.66 you can consider as kilonewton, or those who use American system, it is kip. Okay. Now, what is the shear force? We have to find out the reactions now. Okay. Now we will apply the moment about this x, this point, about B. This is A, this is B, to find out the reaction. So this is the force we do not know. We consider it is VA, and this is VB. The same convention same name we are using in other problems, other cases, in other videos. So moment at this point, we can write down the summation of moment is equal to 0. That is our second equilibrium equation. This is the first equilibrium equation, we get it. This one, the second I am using. Now, summation, you take moment about that. This is a VA times 10. This is, you see, look here. This is what? This force is acting from below, like that. So how it will do? It will rotate it in a clockwise fashion. So consider this is positive. Clockwise is positive. I will explain that what is the positive and negative conventions we use for bending moment and shear force diagram. But for the time being, you consider it is positive, and this force is 8. Keep here at this point, it is causing a anti-clockwise. So it is negative 8.66 times 5 equal to 0, because summation of moment is 0. Okay, what is that now? So VA 10 equal to 8.66 times 5 divided by 10, cancel out this 2, so it is 4.33. You can put the unit as kilonewton or kip, it doesn't matter anything. 4.33. Now we will be using the third equation I am using. They are not in the order, summation, but I am calling it third. Okay. So third equation I am using, summation of vertical force equal to 0. Here we use summation of horizontal force equal to 0. And here we use summation of moment equal to 0. Okay, and now I am using summation of vertical force is equal to 0. That means I have this 10, reaction is 8.66. What is the reaction here? RA, VA, and we find is 4.33. So we get VA then minus 8.66 equal to, and VA is what? VA is, it is VA minus that equal to VB. So we can take this, so VB equal to minus 4.3. So VA equal to 4.33 minus 8.66 equal to 4.33. Minus this here, the minus means this is opposing the 8.33. So this force will be your 4.33 again. 4.33 there. And because VA 8.66 we are considering downward. So if you consider the negative, that means if you consider something like that, VA minus that 8.66 is minus 8.66 equal to VB. So this will be 4.33 minus positive. I get confused. Let us forget about that. This will be more complicated. You can say it is 8.66 minus 4.33 8.66, instead of complicated, make 4.33 equal to 4.33. Don't make it complicated. So this forces is 4.33, this is also 4.33. Upward, this is upward because it is downward, it is upward. This is how it is. Or one more way you can do it, forces equal to total forces equal to total reactions. So it is 8.6 is exactly at the middle. So half will go this side 4.33 and half will go this side 4.33. This is how it is. Okay, it's exactly at the middle. You can, from symmetry, you can put it 4.33. Now let us draw the bending moment diagram or shear force diagram. So it is 4.33, right? And this is also 4.33. In shear force diagram, we have a sign convention. This is positive. That means if we consider from the left, upward force is positive, and if you consider from the right, the downward force is positive. That means if you calculate the values from right to left, this will be the case. And if you consider from left to right, then this is the case. And another one is, that means if you consider the shear force diagram from left to right, so downward forces is negative, upward is negative when you consider from right to left. Okay? So this is the convention we will be using. So let us do one thing here. If this is 4.33, with graphical representation, we say assume this is 4.33 from here to here. Now, there is no load from here to here. Forget about the horizontal load. So from here to here, no load. So this will be constant 4.33. As soon as you reach here, at this point, just left it is 4.33, just left of this section. As soon as you just right of that point, this 8.66 arrives. Push it down. So this value, so this here the shear force is 4.33 minus 8.66. Total is minus 4.33. So this is 4.33. But this is side minus, this side plus. So from here to here, there is no force. It will be constant. There is no force from here to here. So it will remain as this. Then at the end, the 4.33 is upward. We are considering from left to right. So see, upward force is positive, downwards is negative. So 4.33, so this will be negative 4.33. Just left of this is 4.33. Just as soon as you reach this is just right, or just at the point, this is going up 4.33, making it like this. So this is the shear force diagram. At this point it is 0 like that. But actually the shear force at this point is 4.33. Shear force is this point also 4.33. This is how it says. So if you design this beam, for this beam, the shear force diagram is there. So you have to design for 4.33 either kilonewton or kilopound. Depends on your unit. Now let us draw the bending moment diagram. The bending moment diagram is something like this. The bending moment diagram is the force into distance, right? So one thing you should remember, always it is true. You have got a shear force diagram is something like this, right? When the shear force is constant, bending moment is linear. This is the golden rule. Shear force is constant, bending moment is linear. Linear means it follows like this, linear. When the shear force diagram, shear force value is 0, nothing there, I will explain that with a different example. The bending moment is constant at that point. When shear force is linear, bending moment is parabolic, like that. Because the factor, the shear force is governed by F, the force, and moment is governed by F into X, distance. So if you consider X is a variable, here whatever X value is, F value is F is some value, so Wx, so it will be Wx square. So if it is linear, it will be parabolic, 1 degree ahead. So don't get confused with that. Okay. Now let us draw the bending moment diagram. So bending moment diagram is, now we have a convention there. This is positive, this is negative. Okay. So the positive means if you consider from left, it will be bending in a clockwise direction is positive. If you consider from right, moment in the anti-clockwise direction is positive. If you consider from left, this anti-clockwise is negative. If you consider from right, the clockwise is negative. Then what happens if you have a moment like that? It will sag, just like this. So this is called sagging moment. So sagging is always positive. Try to bend. It's a cup. forming like a cup is a concavity upward. You see, this is concave upward. It is always positive. When the bending takes place, so what happens if you apply a moment like that? In case of you have cantilever, here the moment is like this. Here if you have some load there, it will try to bend it like this. So it will be bending like this. So when the concavity downward, or it looks like an umbrella, so this is negative, this is hogging moment. So it is negative. This type of is negative, and when it bends like that from moment, it is positive. You always remember. So here you see you have support like this. Our moment, whatever will be the case, our moment is always positive because it is deflecting like this. Now let us draw the bending moment diagram. Now 4.33, there is nothing in between. You can put an x there, but it doesn't matter. So x, so at this point your moment is 4 into x. But we will straight away go to this point because up to this point there is no change, no force. So this is 5, we know that. 5 meter or 5 feet, whatever it is. So 4.33 times 5 is okay. So 20 So it is 21.65 there. As I told you, there is no force when the shear force is linear. If bending moment, if shear force is constant, you have bending moment is linear. When the shear force is constant, remember that your shear force is like that, right? Your shear force is like this. Your shear force is linear. So shear force is constant from here to here. So your bending moment is linear. And value is 21.65. Then from here also if you multiply by 5, it is the same value you will get. So if you have to join this one, this is your bending moment diagram. This is SF diagram. So this is the very simple case of bending moment and shear force diagram. In the next lecture, I will be talking more about this. We will solve different types of forces, different types of forces on a beam, and we try to see how it behaves and how the bending moment and shear force diagram will look like. Okay, so I think you understand what I am telling you today. Okay, don't get confused. This is the simplest form to find the bending moment and shear force diagram. Why it is positive, why it is negative, I explained that, you understand probably, and we will be following the same principle, same thing in the other problems also. This is all for today. If I solve another problem, it will take longer time. So I don't like to complete it and take a long, my video is longer than normal. So I will close it here. Hopefully you understand what is how to calculate the shear force and bending moment diagram. If I solve more problem, it will be more clear to you, and an exam you can very well can solve this problem and find out the shear force and bending moment diagram. This is all for today. I wish you good luck and you will understand. Probably if you have any doubt, you will understand more later. Okay, this is all. Thank you very much. Have a good day. Appreciate it.